Hey everyone, welcome to this explainer. So today we're chasing what's basically the holy grail of modern computer vision. For years, right, if you wanted to run state-of-the-art object detection at high speeds, you had to shell out for massive, ridiculously expensive GPUs. But get this, it turns out we can now run incredibly accurate, blazing fast AI detection using literally nothing but a standard CPU. No expensive hardware required. We're going to unpack a major breakthrough that actually makes this possible. And to test it out, we've got a really fascinating case study looking at footage from the 2026 FIFA World Cup.
Okay, let's dive into this. Here's our roadmap for today. First, the OpenCV 5 revolution. Second, prepping the YOLO26 brain. Third, the NMS-free magic. And finally, a World Cup CPU stress test. As we go through this, just think of YOLO26 as a highly trained brain and OpenCV 5 as the shiny new engine that lets it run absolutely anywhere. All right, Section 1, the OpenCV 5 revolution, the first major update since 2018. So the contrast between the old world and the new world here is just night and day. Back in the OpenCV 4 days, you were usually bogged down by these really messy dependencies, relying on clunky cafe and darknet importers and older CPU architectures just to get a model to run. But OpenCV 5, which dropped in June 2026, totally changes the game. They completely rewrote the Deep Neural Network, or DNN module, and now has direct native support for ONNX, which is basically the universal file format for modern AI models. Plus, we get a totally rewritten CPU engine with shape inference and operator fusion built right in. Honestly, the beauty here is what's missing. There are no heavy frameworks dragging you down at runtime, no PyTorch, no messy importers. It is just an elegant, entirely self-contained powerhouse. Moving right along to Section 2, prepping the YOLO26 brain by exporting it to ONNX. So before our shiny new OpenCV 5 engine can actually run that YOLO26 brain, we have to translate the model into that universal ONNX language I just mentioned. And the crucial point here is getting 3 very specific Python export settings exactly right. First up, your opset, which is basically the version of your translation dictionary, absolutely must be 12 or newer. OpenCV 5 will straight up reject anything older. Second, you need a static input shape. By locking your image size to 640 and setting dynamic to false, you completely avoid some really frustrating parsing bugs. And third, this one is vital. You have to export with no NMS. Setting NMS to false keeps the model's raw head perfectly intact because YOLO26 is already built to do that heavy lifting itself. Hit those 3 settings and you guarantee a perfectly clean handoff to the engine with 0 messy graph errors. Now, looking at this output actually highlights a pretty fun quirk about how these AI brains work in reality. When the model looks at a frame from the World Cup, it easily spots Lionel Messi on the ball. But, as any football fan will tell you, that bounding box should clearly read GOAT, greatest of all time. Unfortunately, the AI rigidly categorizes him as just a person. And why? Well, it's strictly limited by the Coco dataset it was trained on. Because they never bothered to add a GOAT class to Coco, person is literally the absolute best the AI can do. It's just a great little reminder that an AI is only ever as smart as the data we feed it. Okay, Section 3, NMS-free, simplifying detection and removing the post-processing mess. To really appreciate how much this simplifies things, we need to look at the old post-processing mess. Older models, like YOLO-V8 for example, would spit out this massive, chaotic grid of candidate boxes. We're talking a giant 1 by 84 by 8400 tensor. It was a nightmare. You had to transpose it and then run this heavy, complex algorithm called non-maximum suppression, or NMS, just to filter out all the overlapping duplicate boxes. But thanks to YOLO26's end-to-end design, it emits a beautifully clean, fixed 1 by 300 by 6 tensor. Every single row in that block is already a final detection, with the coordinates, the score, and the class ID. It completely removes the need for NMS. All you have to do is drop the rows that fall below your confidence threshold, say 0.25, and then map those boxes directly back to your frame. It makes the code incredibly, almost beautifully trivial. So what exactly is the engine doing under the hood? Well, there are really just 5 simple jobs OpenCV 5 performs for every single frame. 1, it reads the pixels. 2, it preprocesses them using a function called blob-from-image to get the visual data formatted for the AI. 3, and this is where the magic happens, it runs the forward pass entirely inside its own rewritten DNN engine. Again, no external runtime required. 4, it draws the bounding boxes. And 5, it writes the output. That is the whole shebang. All that heavy pixel plumbing is just handled super efficiently right behind the scenes. Which brings us to the climax here, Section 4, World Cup results on CPU, the ultimate stress test.
we've talked a lot about the theory and the architecture, but now we've got to ask the big question. Does this CPU engine actually hold up to motion blur and the chaotic, fast-paced action of a live sports broadcast?
The answer is an emphatic yes. When we run this on live 2026 FIFA World Cup clips, the results are honestly stunning. Look, broadcast frames are rarely perfectly sharp, right? But the detector holds incredibly tight boxes anyway. Even on a crazy corner kick into a crowded penalty box, it cleanly separates overlapping shirts. When players are sprinting and you get that smeared limb effect on camera, it still accurately boxes the goalkeeper and outfield players. It even tracks the fast-moving ball without breaking a sweat. This robustness comes straight from YOLO26's incredibly varied dataset training, meaning a little bit of broadcast blur rarely breaks the detection. And just to reiterate, this is tracking frame by frame at real-world speeds entirely on a standard CPU. It's wild.
Before we wrap, I want to leave you with this number, 5. Because OpenCV 5 is really just getting started. We've spent this entire explainer looking purely at object detection, but this brand new inference runtime handles far, far more than just drawing boxes. Future workflows leveraging this exact same GPU-free pipeline are going to be tackling complex tasks like detailed human pose estimation and pixel-perfect image segmentation. OpenCV 5 has successfully transformed itself into a serious, self-contained inference runtime that is quite literally democratizing computer vision. You no longer need thousands of dollars in hardware to run state-of-the-art AI. It's incredibly fast, it's completely NMS-free, and it runs right on your computer's standard processor. So, with CPU inference becoming this powerful, this accessible, and this elegant, what will you build next? Thanks for tuning into this explainer, and I seriously cannot wait to see what you all create with this.